Welcome to the lecture number 21 of compiler design. In this lecture, we will go through what is a symbol table and what are the various approaches to symbol table organization. So before going to symbol table, let me ask you some questions, then I will go through symbol table. So now here I have written a small C program. Now I will ask you one thing. Here if I will write printf percentage d comma x. Now you see here I have taken two functions. One is fun, another one is main function, right? So from the main function, let me call the fun function. So let me take a variable over here, integer a, and here let me write k equal to fun, right? So now here let me in the fun function, let me return the value of x. Now you see, you know that every program execution begins from main function. So my program execution will begin from main function. Then you see, I have declared a variable integer I. Then I have declared a variable integer k. Then I have called a function fun. So when you will call the fun function, the control will be transferred to the function body of fun, right? Next, this body will be executed, then the x value will be returned, which will be stored inside k. Is that clear? So now you see, if I will execute this one, so let me compile and run this one, you will see it will print the value of x, that is 10. It will print the value of x, that is 10. So it is taking a bit of time, so please have some patience. So you see the program execution begins from main, then it calls the fun function, then in fun function you have printed the value of x. So what it will do, it will compile and execute, then it will print the value of x. So now you see it is printing the value of x, that is 10, right? So now here let me modify a bit. Let me modify this program a bit. So here you see, let me write printf percentage d, instead of x let me write z. Okay, and let's say the z value is 100. So here you see the z is a global variable. It is visible throughout the program. So whether I want to print the value of z in fun function or in main function, in both the functions the value of z will be visible. So here you see, here let me write z equal to percentage d z. So what it will do, it will print the value of global variable z. So execute, compile and run. So here you see what it will show you, it will show you z equal to 100. So here you see it has shown you z equal to 100. Is that fine? Now let me ask you one more question. Here suppose instead of the value of z, let me print the value of a. So you see a is a local variable to main function. It means what? A will only be visible to the main function. So if I want to print the value of a over here in the fun function, a equal to percentage d a. So now if I want to print this value of a inside fun function, you see it will generate an error, undefined variable a in fun, because the variable a is visible to the main function only, because a is a local variable to main function. Is that clear? Now let me execute and let me compile and run it. You see it will generate an error. You see here it is generating an error. Is that clear? So here let me ask you one question. How the compiler stores this information? A is visible to main function, x is visible to only fun, whereas z is visible to both fun function and main function. That is, z is visible to all the functions that is created within this file. So how the compiler keep these informations? In order to keep such informations, it requires a symbol table. Okay. So now here also you see when I have written k equal to fun. Here what I have done, I have called the fun function. So when you will call this function, the control will be transferred to the body of fun function. So how this transfer happens, or who keeps this information? That is nothing but a symbol table. So today we will go through symbol table. Okay, so what is a symbol table? A symbol table is a data structure which is used by the compiler to keep track of scope and binding information. So scope means what? The region of the program where the variable or name is accessible. Okay, so in the example I have shown you that the scope of X is means the region of program where X is visible is fun function. Similarly, the scope of A is the main function because A is a local variable to main function. It means A can only be visible to the main function. So the scope and binding information, you see a symbol table is a data structure. So data structure means what? Data structure provides a way to store and organize the data in order to facilitate easy access and maintenance. So what is a symbol table? Symbol table is a data structure used by the compiler for what? To keep track of scope or binding information. So scope means the region of the program where the name is visible. Binding means what? When I have called the function, when I have called the fun function from the main function, the control is transferred to the body of fun function. So how the compiler knows these things? So these information are maintained in a symbol table. Okay, so in symbol table, the symbol table is searched every time a name is encountered in the source program. So name means what? Name is nothing but identifier. Okay, identifier. So identifier means what? So identifier means there are, you know that it may be a variable, it may be a array name, it may be a function name, it may be a structure name, it may be a union name, it may be a class name. So wherever you will get the term name, that is an identifier, right? So a symbol table is searched every time a new name is encountered. So when a new name is encountered, what it does? So when a new name or new information about the existing name is discovered, the content of the symbol table changes. Okay, so there are basically three ways for symbol table organization. The first one is the most simplest way, that is a linear list. So the linear list is the easiest way to implement a symbol table. So in linear list, what we will keep? We will keep name and its information. Okay, so first we will keep the name, then we will keep the information, then name, then another information. Then suppose another name 3 comes, so we will store the name 3 over here and the information over here, right? So available is a pointer which points to the location where new information can be kept. So the new names are added to the table in the order they arrive. Suppose first name 1 arrive, so first we have kept name 1. Then suppose name 2 arrived, so we have kept the information of name 2. Then suppose name 3 will arise, then what we will do? We will keep the information of name 3. Okay, so this way what we can do? We can store the names. So now whenever a new name is to be added to the table is first searched linearly or sequentially to check whether or not the name is already present. So if the name is already present, then no need to create a separate record for that one. But if the name is not present, then what we will do? The record for new name is created. So where it will created? It will be created, that will be specified by the available pointer. Okay, and added to the list at a position specified by the available pointer. Okay, so to retrieve the name information or the information related to a particular name, the table is searched sequentially starting from the first record. Suppose I want to, suppose in a program, let's say name 1 is A, okay, name 2 is B, name 3 is C. Okay, it can be anything, right? Name means it may be an array name, function name, or identifier name, anything. It can be anything. It can be identifier. So whenever a name is encountered, what we will do? Suppose we have got a new name, integer B. So here B is the name. So first it will be searched in the symbol table. So how it will be searched? It will first check the first index. Then it will check the second index. So first index B is present? No. Second B is present? Yes, yes, B is present. It means it will not create a new record. Okay. So the names are searched sequentially in the linear list. So if the new name is already existing, so no record will be created, but if the name is not existing, then it will create a new record for that name and it will store its information. Okay, so the average number of comparisons required for search are n plus 1 by 2. So I will tell you how it is n plus 1 by 2. So you see, suppose this is we are storing in a linear list. Let us consider that array. Okay, in an array we are storing the information. So you see 0, 1, 2, 3, 4. So the total number of element is 0 to 4, that is 5. So when you are searching, it may present at the first index. So in that case, it requires one comparison, right? Or it may present in the second index. So if it is present in the second index, so first you will compare the first index. Here you will not find. Then you will compare the second index where you will find. So it requires two operations. Okay. Similarly, if it is found in the third one, so you require three comparisons, because in first you will not find, in second you will not find the name. Suppose you have found the name at third index or second index, so you require three comparisons. Similarly, for n things you require n comparisons, n possibilities are there. Okay, so what is the average of this? So if there are n things you have done or n symbols you have searched, so I will divide it by n. Okay, so 1 plus 2 plus 3 plus 4 plus n is nothing but n into n plus 1 by 2 divided by n. So what you will do? N will cancel out. You will get n plus 1 by 2. So what is the average time or average operations or comparisons required for a successful search? It is nothing but this is equal to n plus 1 by 2. So that I have written n plus 1 by 2, right? But for an unsuccessful search, what is the average number of comparisons? Here you see, so if there are 5 elements, so here it will not be found. So 1 comparison, 2 comparison, 3 comparison, 4 comparison, 5 comparisons. So if 5 elements are there, 5 comparisons are required for an unsuccessful search, means you will not find that element. Okay, so for unsuccessful search, the number of comparisons will be p equal to n. Okay, so I hope all of you have understood how to store or how to organize the symbol table by using a linear list. Now let us go through another efficient way than linear list, that is the search tree. So in search tree what we will do, we will for every name we will create a record, and this record will have 4 parts. One is left pointer, another one is a right pointer, as you are representing the trees, and here you will keep the name and here you will keep the information associated with that name. Okay, so now you see, suppose the name is VAR variable. Okay, so suppose another name comes whose name is ALU. So when you will keep the ALU, you see ALU is alphabetically lower than VAR, so you will keep it over here. So here I will keep ALU. Okay, suppose another name comes, let's say the name is XYZ. So you see XYZ UVWX, so X comes after V, so it will be stored on the right hand side of this record. Okay, so here X, Y, Z, right? So similarly, it will follow the alphabetical ordering. So you know that this is a way to represent the binary tree. So, or we can say that in binary search tree, all the elements on the left hand side are smaller than the root node, and all the elements on the right hand side are larger than the root node. So here what it will show, as we are storing the names, it will see the alphabetical ordering. Is that clear? Now you see, this is a two binary tree. This representation is a binary search tree. Okay, search tree. So what you can do, you can also use a multi-way search tree. Multi-way search tree. like B tree or B plus tree. You can use them to store the information of the symbol tables. Okay. So here how the search will happen. So you see, suppose a new name comes. Suppose the new name is, let's say, ANDA, anda. So how it will search? So first it will keep compare with the root node. Okay. So ANDA is same to VAR? No, those two are different. So whether to search the left subtree or to search the right subtree, you see ANDA is smaller than, alphabetically lower than VAR. So you will have to discard the right subtree. You have to go for the left subtree. So this way you will search for the new names. Okay. So if the name is already found, no need to create a record. If the name is not found, then you have to create a record and add it on the appropriate side, either left side or right side. So now you see what I have told you, the same thing I have written over here. So this is a more efficient approach to symbol table organization. Here what we will do, we add two links. One is left link, another one is right link in each record, and these links point to the record in the search tree. So whenever a name is to be added, first the name is searched. Means if you want to add a name, first you have to search whether that name is already existing or not. So if the name is already existing, no, don't worry. You have already had the information. If you want to update the information, you can update the information. But if the name doesn't exist, then what you have to do? Then a record for the new name is created and added at the proper position in the search tree. Means whether you have to add on the left subtree or you have to add on the right subtree, you have to decide based on the lexicographical ordering or alphabetical ordering. Okay. So here this organization has the property of alphabetical accessibility. It means what? All the names accessible from name I will be, by following the left link, precede the name 1, means alphabetically, that is before the name I. Okay. And all the links or all the names which are larger than the particular node, that will be placed on the right hand side or right subtree of that node. Okay. So the expected time needed to enter n names and to make m queries is m plus 2 log n base 2. So here base is 2 because it is a binary tree. What example I have given, that is a binary tree. If it is a multi-way search tree, then what it should be? It should be m plus n log, suppose it is a k-way search tree, so log n base k, you require log n base k operations. Okay. So now we will go through another more efficient symbol table organization, that is a hash table. So I hope all of you have studied hash table in data structure. So the hash table consists of k records which are indexed from 0, 1, 2, 3 like k minus 1. So first what we will do, whenever a name comes, what we will do, we will apply a hash function to this name. Okay. We will apply a hash function to this name. So this hash function will transform this name to a number between 0 to k minus 1. Okay. Suppose this name, let's say this is ABC. So we will use a hash function, so that suppose it has mapped ABC to 2 index. So what we will do, we will create a record which will be pointed from the 2 index, where we will store the name ABC and the information related to ABC. Is that clear? So in hash table what we will do, hash table is a table of k pointers. Here you see, so the k pointers are numbered from 0, 1, 2 dot 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 k minus 1, which are numbered from 0 to k minus 1, that point to the symbol table and a record within the symbol table. To enter a name into the table, what we will do, first we find out the hash value of the name by applying a suitable hash function. So when we have obtained the hash value, then what we will do, the hash function maps that name into an integer between 0 to k minus 1. Then using this value as an index, what we will do, we search the list for the symbol table records that is built on that hash index. So we will search that hash index. okay, or record built on that hash index. So if the name is not present, then what you will do, you have to create a new record. But if the name is present, no need to create a new record. If you want to update the information, you can update the information. So a hash table requires its complexity is in terms of linear time. Okay, so this is the most efficient way to implement or to organize a symbol table. So I hope all of you have understood what is symbol table and how can you organize the symbol table.